Section 4.1, relations and functions. So our objective for this lesson, I can identify how functions and relations are related. So before we get into the function discussion, we need to talk about what a relation is. A relation is a set of ordered pairs. A set of ordered pairs x, y, okay, where x is the input value, okay, and y is the output. Okay. So basically, a relation is just a relationship between two values. Now, the values don't always have to be numbers. The input and the output don't have to be numbers. They could be colors, they could be people, they could be cars. It's basically just mapping an input to an output. Okay. The set of all the possible inputs is called the domain. So the domain is the set of, sorry, I don't know what I was writing there. The set of all possible inputs is our domain. So the domain is those x's, and the range is the set of all possible outputs. Which we know our outputs are our y. So to help keep these straight, x and y is alphabetical. Domain starts with D, range starts with R, also alphabetical, D then R. D comes before R in the alphabet. So that's how you can help keep those straight. The domain is the set of all possible inputs and the range is the set of all possible outputs. So for example, in a relation would be you input somebody's name and it outputs their eye color. Okay. So name, eye color is a relation. Okay, so name and eye color. You could input a TV show and it'll output an actor on that TV show. Okay, a TV show and then its actor. So, for example, my favorite show is Friends, so I could input the show Friends and it would output Jennifer Aniston. Okay, there's a relation. So input the show Friends and it'll output Jen Aniston. Okay, I could input the show Friends and it would get me out Matthew Perry. Okay, or so forth and so on. Okay, so that is a relation. It's just basically kind of relating two things together: the show and the actor that's in it, the person and their eye color, the person and their age, so forth and so on. Okay, sometimes relations are numbers. Numbers are sometimes easier relations because we can come up with equations for them. But so here in this first task, we're going to consider this relationship. So here is our relation right here. Oh, sorry, wrong one. So here is our relation right here. Again, that is my input. So when I input a 5, I get out a 2. So the 5 is my input. So we want to find what are the elements of the domain for these ordered pairs. So the domain, again, is the set of all possible inputs. So we want to look at my inputs here. So to find the domain, input of 5, 4, 3, 2, 7, and 4. So we're going to go ahead and list this as a set. We'll use that curly bracket. And we tend to list the domain from least to greatest, just to kind of organize it a little bit. The smallest domain up there is a 2. And then, so there's my 2. We also have a 3. We also have 4s. We have a 5. We don't have a 6, but we have a 7. So there is my domain, 2, 3, 4, 5, and 7. That is the set. In that set of numbers, I get all possible domain values there. There's my 2, my 3, my 4, my 5, and my 7. So now if I want to find the elements of the range using a different color. So the range is the set of all possible outputs. So again, we'll use a curly bracket to talk about a group of numbers, and it looks like that smallest range value is a 0. Got that 0 right there. We have a 1, we have a 2, a 3, a 4, and a 5. A 0, 1, 2, 3, 4, 5. Okay. So there is my range. It's the set of all of these possible outputs are in this list right there. So next, we're going to talk about what a mapping diagram is. And we will reference this in our practice. A mapping diagram is basically this guy over here. It's a list. There is all of my domain values are right here. 2, 3, 4, 5, and 7. And then all my range values are right there. 0, 1, 2, 3, 4, 5. And then we have, the reason it's called a mapping diagram is it shows the 5 goes to the 2. So basically my ordered pair 5, 2 is there in that mapping diagram. My ordered pair 4 to 1 is right there. 3 to 0 is right there. It actually has an arrow that shows one goes to the other. Okay. So that mapping diagram shows how the elements in the domain and the range correspond to one another. How does the element 4 in the domain different from all the others? So if we look at this domain of 4, how is it different than all the others? Okay. If we notice, each one of these, 5 only has one arrow coming from it. 3 only has one arrow. 2, one arrow. 7, one arrow. 4 has 2 arrows coming from it, because an input of 4 actually goes to 2 different outputs, to 1 and to 3. So how is it different? The input 4 maps to 2 different outputs. That's how it's different. The input of 4 maps to 2 different outputs. The outputs of 1 and 3. So that 4 goes to both 1 and goes to 3. Okay, so that's slightly different than the other inputs. Okay. All right, so now I want you to go ahead and pause the video and think about this question. Why are there only 5 elements in the domain, even though there are 6 ordered pairs in the relation? Why are there only 5 things in here? 1, 2, 3, 4, 5, when we actually have 6 things up here? All right, now, okay, so now we need to talk about, so hopefully you gave some thought to that. Okay, now we need to talk about a function. So a function is a special type of relation. Okay, so if a relation has this characteristic, we call it a function. So it's a special type of relation. So a function is just a relation that every domain value, again, our domain value is those inputs, corresponds to exactly, and I'm going to put that in bold, exactly 1 range value or output. Every input goes to only 1 output. So this relation up here that we were talking about in task 1 is not a function. This guy up here, this guy here is not a function, because the input of 4 goes to 2 outputs. Not a function. It's still a relation. Like, we have relations, it's just not a function. So you can use a mapping diagram to determine whether a relation is a function. So if we look here, we want to describe how the mapping diagrams of the 2 relations shown are different. Okay, so if we look at these, 1 goes to 6, 2 goes to 9, 3 goes to 12, 4 goes to 15, and 5 goes to 15. Every single one of these only has, every input only has 1 arrow. every input only has one arrow, only goes to one output. Okay. Now, I do have an output of 15 that both 4 and 5 go to. That's okay. It doesn't say anything up here in a function about the output only having to go to one input. Okay, it's every input goes to only one output. Okay, whereas this one, if you notice here, this one, if we look at 2, the number 2 has 2 arrows. Input of 2 has 2 arrows. It goes to both 4 and to 10. So which mapping diagram represents a function? Explain why. The first one. Why? Every input has only one output. Okay, so then that means the second one is not a function, since an input of 2 has 2 outputs. The 2 outputs are 4 and 10. The input of 2 has 2 outputs, 4 and 10. Again, yes, 10, 5 goes to 10 and 2 goes to 10. That's okay. You can have 2 inputs with the same output, but they can only go, each input can only go to one output. Okay. There are other ways of showing relations. Okay, up here we talked about one way of showing a relation is just with ordered pairs. We can list out all the ordered pairs. Another way is we can map it. We can draw a nice little map. Another way here is we can use a table that shows my x's and how they go to my y's. So we can also use a table of values to determine whether a relation is a function. Again, these are both relations because an input goes to an output. That's all you need to be a relation. An input goes to an output. But to be a function, every input can only go to one output. So let's go ahead and identify that. It says what y values are associated with an x value of 2 in the first table. So let's look at an x value of 2 right there. The y value is 2. Is that the only 2 we've got? Look at all the rest of them. Yep, I think that's it. So what y values? So that first one, it's a y value of 2. So for the first table, we have the 0.22. Okay. Second question is what values of y are associated with the x value in the second table? So if we look at the second table, we have an input of 2, output of 4. But if you look at all the rest of these, 0, 3, we have another one there, input of 2, output of 5. So in the second table, we have an input of 2, output of 4, but we also have an input of 2, output of 5, which that right there means this guy is not a function because my input of 2 has 2 different outputs. So explain how you can determine whether a relation is a function by considering the table values. We want to look at the x values, okay? So what do? We look at the x column for any repeating inputs, for any repeated inputs, to see if they map to different values, map to different outputs. Okay, now, just a word of caution. Just because an input repeats doesn't necessarily mean it's not a function. I have to look at the outputs and make sure they're different. So if this was, instead of a 5, this was a 4, it would still be a function because an input of 2, output of 4, input of 2, output of 4. What makes it not a function is the fact that those two numbers are different. The fact that this 4 is different from this 5 is what makes it not a function. Okay, not the fact that they repeated, but the fact that they repeated and they were to different values. Okay, so we've looked at how to tell if a relation is a function from a mapping diagram here. Again, we're looking for that input with two separate outputs. From a table, input with two separate outputs. That means it's not a function. You can also look at the graph. So the vertical line test is a graphing tool to tell if a relation is a function. Okay. Basically, any vertical line can only hit 1 point. 1 point on the graph to be a function. Okay. So I envision a vertical line. So here I have two graphs. Two graphs of relations are shown. If I have a vertical line and I take these vertical lines and I cut through here, basically I cut through my entire graph, it can only hit 1 point on the graph. And I can tell as soon as like here would only hit 1 point, that point right there. But as soon as I go farther to the right, like let's say this point, like if I draw a line through right here, it hits 2 points. Since it hits 2 points, I know it's not a function. Okay, so is there at least one vertical line that crosses the first graph more than once? Yes. So this first graph is not a function because it hits 2 points. And basically what that tells me is that here my input of 1, because of course my x value here is 1, this tells me an input of 1 has two outputs. This value up here, which looks like it's almost 2, not quite, and this value down here, which looks like almost -2, not quite. So it has two outputs. Whereas on this next one, if I do a vertical line, it only ever hits one spot. So for the second one, only hits one spot. This one, it's a function. And this may look like it's going to keep going straight. It doesn't go straight up. It always has enough of a curve so that my vertical line only ever hits one spot. Okay. So this next bit we talk about, a vertical line crosses the x-axis. So like this vertical line here, this vertical line right here, it crosses the x-axis, right? There's my x-axis right there. Okay, how does this test help you to determine whether every domain value is paired with exactly one range? Kind of what we said here. It's telling us that input value, since it hits in two spots, it has two output values. Okay. All right, so now we need to talk about our dependent and our independent variables. Okay, so if a function, if an ordered pair, let's say if we have an ordered pair xy, if my ordered pair xy has a pattern, okay, it can be expressed with an equation. And we like things that can be written with an equation because it makes it easier to analyze that pattern. So if my ordered pair xy has a pattern, it can be expressed with an equation. For example, let's say that my output is always one more than my input. Okay, so if my output is always one more than my output is always one more than my input, I can write it as that equation, y equals x plus 1. Okay, because my y value depends on what my x is, the dependent variable is my y. Dependent variable, in this case, is my y value. Oh, what am I spelling? I don't know, guys, sorry. My y value, since it depends on x. My x is my independent because I can just pick an x to put in and see, and depending on what x I put in, it changes what my y is. Okay, so my independent variable is my x. It doesn't depend on my y. Okay. So to help in identifying, if I had multiple equations, y equals 2x plus 5, y equals x plus 6, so forth and so on. I had my y equals x plus 1, and I asked you to put a 6 into that equation. Which one am I talking about? Okay. Do I want you to put a 6 into this one? Put a 6 into this one? Or put a 6 into this one? Okay. We don't really know. And that is why we have something called function notation. Okay, function notation is basically you name a function a letter. So function notation is you name a function with a letter. So instead of giving it a name like Fred or George or Harry, we'll give it a letter, normally F, or sometimes G or H, or any of our letters, basically any lowercase. We always use lowercase, any lowercase letter. No, I need to write letter again. Any lowercase letter. We would call it F, we would call it G. Okay, and then we use function notation, which looks like this. Okay, be careful. This is not a multiplication. This right here is not multiply. What this means is this is asking me to find the value of F at X. My X there is my input. And I want to input that function into the F function. So F there is the function's name. And this is telling me I want to input an X into a function named F. Okay? Or we simply say F of X is the shorter version of how to write that. So here, when we were talking about this function, my function rule, this is my function rule. The function rule would be this guy right here, the X plus 1. So my function rule, like X plus 1, is the function rule. It's telling me what to do to my X. Okay, the function rule tells me what to do. Tells us what to do. What to do to X to get to Y. What do I do to my input to get to my output? Okay, so in this case, my function rule is X plus 1, and we're going to name him F. So I would say, okay, F of X equals X plus 1. So this tells me to find the value of F at X, I take X and add 1. It's telling me what I do. This is my rule. Okay. So this function rule basically defines this function. Okay. So really, this is very similar. We're replacing this looks very similar to my Y equals X plus 1. So at Y and F of X can be used interchangeably. So instead of writing an ordered pair XY, I could write an ordered pair X, F of X. Ordered pair. Okay. So again, my X here is my input, but now my F of X is my output. It basically just gives it a name. It tells it that I'm putting it into that F function. Okay. So you can determine the value of a function by substituting a given value for the independent variable. Again, that independent is my X. So here we have an application problem. We have a ball is dropped from a platform 30 feet above the ground. The ball's height in feet above the ground can be modeled by this function. Okay, so let's go ahead. First of all, let's look at this function. Here's my function. And it's in function notation. So H, the ball's height, is H. So here, that is the ball's height. I take negative 16 times t to the second plus 30, where what is t? T is the time. So this t right here represents the time. Or this t right here represents the time. So it's the height at a given amount of time. In seconds, our time is in seconds, and our height is in feet above the ground. Feet above the ground. Since the ball was dropped. What is the independent variable? The dependent variable. Okay, so first of all, my independent variable is again my input. I input, this is telling me my input right there and what I do to it. I take negative 16 times t to the second and add 30. So my independent variable in this case is my t time. Okay, so then what is my dependent variable? Okay, this is where it's interesting. Your dependent variable isn't actually just one variable, it's h of t. It's my output right there, my output, h of t, which is the height. So if I know the time, I can find the height. So now what does, and again, this is read as h of 1. So if you look at my equation, it's h of t. Here my t is replaced with a 1. My t is replaced with a 1. So 1 is the time. So this is saying at time 1 second, what is the height? Because it's h of t. Or a better way of saying it is it's the height of the ball after 1 second. So it is, that's a better way of saying it. It's the height of the ball after 1 second. So my h of 1. So describe how to find h of 1. Put 1 into the function rule. Put 1 into the function rule for t. So how that would look, h of 1 is equal to, now I come up here, I grab this function rule, I replaced my t with a 1. So I replace that t with a 1. So it would be negative 16 times 1 to the second plus 30. So order of operations, I have to do 1 to the second first. 1 times 1 is 1. So negative 16 times 1 plus 30. Negative 16 plus 30 is 14. And again, this is the height, so 14 feet. So after 1 second, so h of 1 equals 14. What this tells me is the ball is 14. The ball is 14 feet high after 1 second. That is what this means. Okay, so the ball is 14 feet high after 1 second. Okay, you can also determine the value of a function by using the graph. Okay, the graph of the function g below is a set of all points x of g of x. So not really below, to the right. I put it over here to the right. So there's my function. Okay, so every single ordered pair on here is an ordered pair of this function, where x is the domain of the function. Okay, so basically here, and they give us an ordered pair, an input of 2, because here we're counting by 2s, gives me an output of negative 4. So I have the point when x equals 2, negative 4. So we can write it that way. G of 2 equals negative 4. So first step, what is the domain of the function? Again, the domain is the set of all possible inputs, which in this case is my x's. My x-axis, my x-axis is my left to right. Okay, that's my x-axis. And this doesn't have just particular dots. It's all connected. So that tells me, and it has an arrow here and an arrow here, which shows me going to the right forever, shows me going here to the left forever and to the right forever. So, and it's hitting every point in between, like every single point in between here is getting hit. It's a solid line. So that tells me that my domain is all the numbers. Because I can put in a 9.5. Sure, I get an output right there. Okay. I can plug in a 0. Sure, I get an output right there. I can plug in a 500. Sure, I'd get an output way the heck out here. Okay. So basically my output here is all the numbers. Okay. Any number I can put into this. So how we say that is all real numbers. There are some numbers that are not real. We just don't talk about them yet. So we want to specify it's all those real numbers. Okay. So for the next one, for the given graph, determine g of negative 2. That's my input. I'm looking for g of negative 2 would be the output when my input is negative 2. So to find g of negative 2, I look at my graph for an input of negative 2. negative 2. I look at my output. It looks like, so I come over here, input of negative 2 gives me that ordered pair right there, which will give me an 8. So G of negative 2 equals 8. So this tells me I would have the ordered pair negative 2, 8. Input negative 2, input, output 8. So what's G of 6? Again, when I put in a 6, 6, 2, 4, 6, I get out a negative 8. So that tells me I would have the ordered pair 6, negative 8, input of 6, out of negative 8. Okay. Describe how to use a graph to locate a function value for the given value of x. What do? We find that x, right? So use the graph to find, okay, find the x value on the graph. See what it maps to. See what y value or f of x value it maps to. All right, we have one last problem, an application type problem. So here we have an artist spends an afternoon making bracelets using beads she already has. She uses beads for each bracelet. The remaining number of beads are, so R is representing the remaining number of beads in her supply, can be modeled by the function. I'm going to write the function down here. R of B equals 90 minus 15B. Again, my input here is my B. My input is B. There's my input, in. Where B represents the number of bracelets she makes. So my input is the number of bracelets. And the output, which is R of B, that whole thing, is the output. And that's the number of beads left. Okay. Because where B represents the number of bracelets she makes. Find and interpret. Interpret. Tell me what it means. R of 0. So this tells me I want to put in a 0 into my function rule. My function rule is this guy right here, that 90 minus 15B. So I would take 90 minus 15. My B is now 0. So 90 minus 15 times 0 is 0, which gives me 90. So I would write R of 0 equals 90. I need to interpret it. 0 is representing the number of bracelets. That's my input, number of bracelets. So basically this means if she makes no bracelets, if she makes 0 bracelets, she will have 90 beads left. It also wants us to find R of 3. Oh, sorry, R of 3. So 90 minus 15 times 3. So 90 minus 15 times 3 is 45. So 15? Oh no, 45. Sorry. Okay. So if she makes 3 bracelets, she has 45 beads left. Okay. So she has 45 beadlets. Then we want to graph R of B. Okay. First thing I notice is when I want to graph this, I need to figure out where to put my axes. I can't make a negative number of bracelets, and I also can't have a negative number of beads. So this tells me that basically I'm dealing in quadrant 1, or I can only do positives. Okay, so I can only do positives. I have to get all the way up to, so we know, I'm going to go ahead and create a table. We have B, R of B. We know we have the point 0, 90. So I need to have the point 0, the ordered pair 0, 90 on my graph. We also have the point 3, 45. So we need to find a scale. to use for this. So I think since I have to get all the way up to 90, can we count by fives? Let's see. 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, 75, 80, 85, 90. Perfect. So 90 would be, there's 10, 20. I'm just going to mark every two as 10, 10, 20, 30, 40, 50, 60, 70, 80. There's 90 up there. And so we can mark a few more out, 10, 20, 30, 50, 70. Okay. Okay. But then on my x-axis, I don't need to count by like fives or tens because I'm just going 0, 1, 2. So I'm going to go ahead and I'm just going to have every two be 1, 2. Again, when you're graphing, you need to mark your axes. So 4, 5, 6, 7, 8, 9, 10. There's 10. So forth and so on. I don't know how many bracelets we can make, but we're just going to go ahead and mark them all out. Okay. So if we go ahead and graph these, we have the point 0 and 90. Point right there. Okay. We have the point 3 and 45, which would be right there. Okay. Now you might be tempted to, connect the dots. Okay. I'm not going to make half a bracelet. So I can't include the points in between like 0 and 1. So I'm going to have to go ahead and come up with the rest of these. So if we put a 1 in here, R of 1. So we'd have 90 minus 15 times 1. So 90 minus that 15 gets me 75. So I'd have the point 175. Okay. And then, so if we keep going and I have the point 2, R of 2, 90 minus 15 times 2. 15 times 2 is 30, so that would give me 60. Hey, after a while, you start to notice a pattern. 260. It goes down by 15 each time. Okay, so I can go ahead and I keep going down by 15 each time. 5, 10, 15. Oh, wait, nope. 4, 15. Why it's doing that. And then we have 5, 10, 15. 5, 10, 15 puts me here, which gives me here at, that's the point 4, 5, 6. Okay, so there's my graph. Okay, again, it looks very linear. Might be tempted to come in and connect the dots, but again, I can't make half a bracelet. I wouldn't make half a bracelet and see how many I have left. So it doesn't make sense to connect the dots in this case. So there is my graph. We graphed R of B. There is my graph, R of B. There is my graph. I can go ahead and mark off these points. And one thing I can tell from this graph is I can only make up to 6 bracelets. After 6 bracelets, I'm out of beads.